All right, hello everyone. Welcome to the problem session for what is this hot lecture 11, I think, the worksheet 11. So in the EU time zones session earlier today, I guess they covered I think problems 1, 3, and 5. So I'm gonna do the natural thing and do 2, 4, and 6. I think they also maybe covered 6A. Yeah, so in this session, I'm going to be doing 2, 4, and 6. And my guess is that we're going to be posting both recordings. So you should be able to get the solutions explained out in more detail if anything is, yeah, in addition to being able to read the solutions that we posted online already. And of course, if you have any questions, feel free to come to office hours and get that cleared up. So let's go ahead and let me see what I want to do. Yeah, so let's go ahead and let me start by just mentioning really quickly what is the idea behind univalence. So this is hopefully a familiar concept to you by now. And by the way, feel free to interrupt me. Yeah, feel free to interrupt me if you have any questions or if anything doesn't make sense. I'll try to keep an eye on the chat, but if I don't see it, then definitely do chime in. So yeah, so let me talk about univalence. So the kind of usual way of presenting it is that we can always, even in non-univalent type theory, yeah. Let me know if you can't read this or if these are kind of light colored. So let me know if they're not too visible enough. But so even in non-univalent type theory, we can define this map equiv-eq or equiv-eq, so if I have A and B in the universe are types, then if I have a proof of A equals B, so this is an element of my identity type, then I can turn that into an equivalence. A is equivalent to B. So this is not assuming univalence. This is just something that we have, and of course we define this by path induction. So we kind of implicitly here I have pi, A, B in the universe. And so I have a free endpoint and an identification as my inputs. And so that allows me to define this. If I can just define it for REFL A, then I will have defined it for all B and for all A equals B. So this is our usual path induction. And so the definition that we give is that equiv-eq of REFL A, and hopefully this is really, this is very much review at this point. So we define that to be the identity function on A, which is an equivalence. And so then this is sufficient to define equiv-eq. And so the statement of univalence, so now univalence says that equiv-eq is an equivalence. And so this is, this makes this an equivalence. And so of course what that means is that we get an equiv from A is equivalent to B to A equals B, such that the composition of, so both compositions, so if I do equiv after equiv-eq, then that's going to be equal to the identity function on this identity type A equals B, and the other way around as well. Okay, so Yeah. Were there other facts I wanted to recall? No. Okay. So this is our kind of background is that univalence says that we can replace or that we can pass between equivalences and equalities as needed. And so therefore, if two things are equivalent, then they are in fact identified, and therefore identical things have all the same properties. And so if I prove two things are equivalent, then they have all the same properties. And so we univalent type theory is just different ways of making use of this fact. Okay, so let's state what we want. Yeah, that works. So the statement of 2, so 2 has several parts. So 2a is as follows. So what we're assuming is that we have a type family P, and I'm going to be writing the universe as U like this, which is kind of how we've been doing it, I think, more in the lectures. But in the solutions, it's written as type. But those are just the different notations for the same thing. And then we have an equivalence. And so then if we have a little p, which is a term of type A equals B, this identity in the universe, then what we're asked to prove is that if I do app p to, sorry, this is capital P, and this is little p here. So if I app p to little p, then remember what app does is it takes an identity in this type in the domain of a function and turns it to an identity in the codomain of a function. And so app, or I'm not going to write that, but app pp has type p of A is equal to p of B, again, identity in the universe. And so if I have identity in the universe, then I can apply I can apply equiv eq to that identity to get a equivalence. So if I do equiv eq of this identity in the universe between p of A and p of B, then that gives me an equivalence between p of A and p of B. But what I can also do is I can do the transport. I can transport this type family P along this identity P. So remember that if remember transport of capital P, this type family over little p from A to B, A equals B. Remember that that gives me a function from P of A that transports it into P of B. So I transport along this equality from things in P of A to things in P of B. And then, of course, I can do the transport of P inverse from B equals A, and that's going to go from P of B to P of A. And so you can check that the compositions of these two are going to end up being the identity functions on P of A and P of B. And so this is an equivalence between P of A and P of B. And so we're going to call that equivalence P star, little p star. So this term I've written here is an equivalence between P of A and P of B. And this here, this P star I've constructed using these transports is also an equivalence between P of A and P of B. And so the problem 2a asks us to identify those. Everyone with me so far? Okay, great. So so let's go about this. So, and the way we're going to do this So we want to show this equation, and we want to show this equation for essentially for all. Let's see if I can write this for all A in the universe, for all B in the universe, and for all is also for all P, but I'll leave that off, and for all little p of A equals B. And so again, what I'm doing here is I'm trying to do, since I have a free endpoint B and an identification here that I'm taking in as inputs, then it suffices to define this by path induction. And so really, let me change color here. It suffices to give a proof that equiv EQ of app P of, so we just do P for REFL, REFL A, prove that that is equal to REFL A star. So we're just doing path induction. So it suffices to do it just for where B is definitionally equal to A, and where little p is REFL. And then that will define it for the whole thing. And so this is a lot easier to do to prove this side. So the first thing to, let me get a new page for this. So we're just going to calculate this one out. So so if I do equiv EQ of app P of REFL A, so that's my left-hand side. The one thing to remember is that the definition of app itself is defined by, so let me just add this really quick to over here that I should have written this down, that app P of P has type P of A equals P of B. And so so app was defined by path induction as well, path induction on this little p. And so it was defined that app of REFL is REFL. So so P of A is equal to P of A. That's REFL of P of A. And so that's definitionally equal. So I'm going to write a dot equals. So this is dot equals to equiv EQ of REFL PA. And then, so that's my first step. And then we can go for that. And for this, we can just go back to, I just took it away, but the definition of equiv EQ. So equiv EQ is also defined by path induction. And so that means we get a judgmental equality for when I apply it to REFL. And in this case, it's the identity function. And so, so this is also going to be judgmentally equal to the identity function on P of A. So if you apply equiv EQ to REFL, you get the identity function. And then, so remember, we're trying to prove this. So REFL A star, so that's really, that's the forward direction of this equivalence. So it's the transport, transport along P of REFL. And again, transport is defined by path induction. So transport of REFL needs to go, so REFL is A equals A, and so transport of a P on REFL needs to go from P of A to P of A. And so that is, and so transport of REFL is going to be the identity function on P of A. And so we also get this I'll write this as refl star, or yeah, refl a. Sorry, this is modulo that screw up there. This is equal to refl p of a star. No, I'm sorry. I wanted refl a. Okay. Final answer is refl a star. So refl a star is transport along P of refl, and so transport of refl is refl. Transport of P is transport of refl is the identity function on P of A, and so that's how I get this last judgmental equality. And so this, the problem statement only asks for a propositional equality between these, these two things, but actually they end up being judgmentally equal, so we can just use, again, refl. Okay, hopefully that still made sense modulo minor screw-ups. Yeah, any questions about that? Okay, so seeing none, I'm going to go ahead and move on to part B. So part B asks us, asks us to kind of lift these operations that we have on paths, namely concatenation and inverse. It asks us to kind of lift those to truncated paths, and specifically paths in the universe. So, so what it says is that if I have, so this is 2b. So if I have A, B, and C, which are types, and I have then what we want is we want a concatenation operator, which takes a merely A is equal to B. So the propositional truncation of A equals B to propositional truncation that B equals C to the propositional truncation that A equals C. So we're concatenating paths, but modulated by this truncation. So there's kind of truncations happening. So the usual path concatenation operator has exactly this type for the universe, except without the truncation bars. And so we just need to make sure that it passes to the truncation. And then we also have the inverse operation on paths. So that takes a that takes A equals B and gives us merely that B equals A. Okay, so this one is the one that's worked out in the solutions. So yeah, the written solutions spell out how to do this one. It says that this version is a little bit easier, but I'm going to go ahead and do this version just for just for demonstration. And so I'm going to do this part for demonstration. So we want to define this symmetry operator on truncated paths. And so the construction of this is going to be relatively easy because remember that the deal with mapping out of truncations was that we have this universal property that if I am mapping into a proposition, and this right here is a proposition, this truncated B equals A, but mapping into a proposition, then I can effectively pretend to drop these truncation bars and just work with the data itself and define a function into there, and then I'll get my truncated function. So the kind of a picture of that was that if here I have my universe, and here I have the universe of propositions, so it's a kind of a sub-universe. And if I want to define, so here's my truncation of A equals B. Sorry, I'm drawing this a little bit. Yeah, I'm drawing this a little bit too small. Let me, not giving myself enough space here. But so, yeah, so this was the universal property of propositional truncations truncations. I'm actually going to write of the propositional truncation because we're kind of assuming a given one. But yeah, so we had the universe, and then we had the universe of propositions, which are only some types of propositions. Other types are not propositions. And so I wanted to, so truncated A equals B is a proposition, and truncated B equals A is a proposition. And what I want to do is I want to define a map of this shape. So I want to define a map that says that if propositionally A is equal to B, then if A equal B is inhabited or is merely inhabited, then I want B equals A to be merely inhabited. So it's the truncated version of this. And so the universal property says that the way to do this is to go from the untruncated type, so A equals B, and define a map here. So just working with the data directly, A equals B into this proposition B equals A. And then we had this map, which is which you might write as eta, or it sends P to, I'd say it sends P to single bars P. And so we get the universal property was that for every map here, there exists a unique map here such that this triangle commutes. So that was how propositional truncation worked. And so the upshot of this is that if I want to define a map like this, if I want to define a map from truncated A equals B to truncated B equals A, then I just need to define a map from untruncated A equals B to truncated B equals A. And that's pretty easy to do. So I'm given a, here, actually, I can write it on the same page. So let me erase this, scratch this out. And so, yeah, I want this this map. And so it's pretty easy. So if I have so the map I want from, use that one. So, so the map I want A equals B to truncated B equals A, then I will just take a P of type A equals B, and I will map it to, what I'll do is I'll flip it around, B equals, so P inverse is B equals A, and then I'll just stick it inside the truncation using this arrow. And so that defines a map from A equals B to truncated B equals A, and then I can use the universal property to go from this to this. And so that's my map. All right, so that's part B. And then, yeah, it's the similar story. You just kind of do this trick twice in order to define the other one we wanted, which was the right here, this composition. So from now on, I'll just kind of write I'll just use these as on truncated path types as well, as if they were just regular path types, because this is well defined. All right, finally, let's do part C. So we just need to show part C is real quick. So we want to show that so we have a type family. So these past two were for or the part 2A was for generic type family P, but now we have a specific type family from U to U, which takes the type X and sends it to the type truncated A equals X. So this is a type family. And so given the type family, so maybe I'll call this, Yeah, I mean, so if this was our type family P, so P of X is equal to A equals X, then a natural question would be, what is app P of some little p? So if I have an equality between types X and Y, what does, so this would be, so if P is X equals Y, then this would be that truncated A equals A equals X equals truncated A equals Y. So we need to say what is this? What does this do? And so so remember in part A we proved that that app of a type family like this is just equiv EQ. So up to univalence, it's the same thing as this this P star. And so so if we can say what P star is, we can say what app is. And the claim that is made in part C is that so if I have some P from that says X is equal to Y, so this is a identification in U, then remember that P star is going to be an equivalence. It's going to be an equivalence, right? It's going to be an equivalence between P of X and P of Y. So this is going to say that A equals X. So there's going to be an equivalence and A equals Y. It's going to be equivalence between A equals X and A equals Y. And so, so the problem claims is that that this is defined as P star of Q, where Q is a truncated A equals X, that this is the same as just post-composing with Q. Or sorry, pre-composing. Pre-composing with this kind of truncated. It should be P. So this is P. So what it says is that if I want to define what P star of Q is, so if I have a Q that says that is truncated A equals X, then P star of Q should say that truncated A equals Y. And so the claim is that that's achieved by taking P, which is X equals Y, and then sticking it into the truncation, so truncated X equals Y, and then using our truncated, truncated concatenation from a minute ago, concatenating that with Q, which is that A equals X. So A equals X, and then X equals Y, that gives A equals Y. So that's the problem statement. And this is actually a little bit trickier to state than it is to prove, because the proof is really quick. The proof is just observing that these are both terms of type truncation A equals Y. So whatever P star of Q is, it has to be a term of A equals Y. And then this is a perfectly good term that we can form of type A equals Y. So this is a term of type A equals Y. And then all that we need to prove this then is just noticing that these two are this type A equals Y is a proposition. And so any two terms of this type have to be equal. And so we might as well define P star of Q to be Q dot, or it's equivalent to define it as that, because these are both elements of proposition, so they have to be equal. Okay, that wraps it up for part two, or for question two. So I'll pause here, see if anyone has any questions. Otherwise, I'll go ahead and move on to problem four. All right, seeing none, I guess I will go ahead and move along. All right, so problem four. So problem four is, these can tend to be rather hard problems, coming up with a counterexample of various claims. So the setup for problem four is that we have we assume that we have some type family B over A. So A is a type. A is a type, and B is a family of types over A. So this is the kind of thing that we can form dependent functions on, of course, and dependent pairs. And so the claim is that, and I'm going to read this under kind of a logical interpretation. So I'm going to say that if not for all A in A, B of A, so not for all A, B of A, then there exists an A in A such that not B of A. And so what kind of makes this tricky is that if you've really only ever seen classical logic in your life, then intuitively you should feel like this is true. That if it's false that for all x b of x, then that should mean that there's some counterexample that refutes b of x. So this is a classically true, if we read this as a for all and there exists in classical logic, this is going to wind up as true. And so it might be, it might be kind of difficult for one's intuitions, or at least, coming from a classical logic background myself, it was initially kind of hard for my intuitions to kind of make sense of how this could be false. But of course, as we've covered in so far in this course, homotopy type theory is not a classical logic. It's not a non-constructive logic. It's a constructive logic. It's a logic where in order to prove an existential statement, we need to supply an actual thing. And so in particular, this is not going to be a tautology in HoTT that if not for all, that implies there exists a counterexample. And so the fact that this is classically true, but not in HoTT should kind of indicate to you that we're going to need to use some structure that is specific to HoTT. So we're going to need to use something kind of HoTT-like. And so the example that the book uses, which I think is probably one of the simplest possible examples of this, is using this type BS2. So let me briefly review what BS2 is. So the definition of BS2 is that so I think the one that Egbert gave in lecture on Wednesday is that BS2 is defined to be the type of types, so X in the universe, that are equivalent to the finite set of two elements. But it's important to note that we're doing the merely equivalent, merely this propositional truncation around the fin of 2 is equivalent to X. And so, so the trick, so this is intuitively, this is the universe of two element sets. And so we proved an important lemma in lecture the other day, or I guess yesterday. I can't remember if it was yesterday or if it was Wednesday, but we proved an important lemma that says that there's no function of this type. So there's no function from x of bs2. So when I write x of bs2, I mean that x is the underlying x is the underlying set of the so this is, an element of bs2 is technically a pair of the type and the inhabitant of this propositional truncation. But if I just write x of bs2, I just mean that's the first component. So there is no function which takes an element of bs2 and produces an element of that type. So the kind of the intuition here is that the intuition here is that these are two element sets, and so each of these is inhabited and has a thing, but we don't have a uniform method for picking one of the two elements. So we just have a mere proof that there are two elements, but we don't have a method for picking one in particular. So this type is uninhabited, and so we could say that it is our lemma here is that this is equivalent to the empty type. So that's going to be an important fact in this proof. And then another point about BS2 that we're going to use is that so let me write this as so write this as BS2. So let me recount the definition here again. So just rewriting this again. It's x in u such that merely fin of 2 is equivalent to x. So I'm gonna massage this into a slightly more workable form. So one thing I'm going to do is so fin2, of course, is equivalent to bool. So just because I like the names of bool, I'm going to replace this as merely bool is equivalent to x. So yeah, I'm going to just replace fin2 with bool. But then the more substantial change that I'm going to make here is that instead of writing this as an equivalence, I'm going to use univalence and write this as a equality. So since bool, this type bool equivalent to x by univalence is equivalent to the type bool equals x, then I can then their propositional truncations are going to be equivalent as well. So that's a lemma we proved. And so I'm going to instead use this as I'm going to instead kind of pretend that BS2 is defined as x and u such that bool is equal to x. So that'll make it more convenient to work with. So this is the kind of the joy of univalent mathematics and mathematics with a well-defined notion of equivalence, is that I can make these kinds of useful substitutions and work in a more convenient form. And so we'll see why this is going to be more convenient than working with the direct definition. Okay, so what I want to show is so I want to show that there is a refutation of this. So I need to cook up a type. I need to cook up a type A and a type family on A such that there is no term of this type. And so the A I'm going to be using, as I've kind of hinted here, is going to be BS2, and the B I'm going to be using is you see right here is just the type itself. So so I'm going to say that A is going to be BS2 for my counterexample here, and B of so BS2 is some set X and some inhabitant phi of merely x is equal to bool, that's going to be defined as just the type x. So b of x is x. And so now this becomes that not, so yeah, substituting these in, x of bs2, x goes to, so I want to show that that gives me x in bs2 such that not x. So I want to show that this has no, I want to show that this type is empty, that there's no, there's not, I want to refute this. So I want to show that there's nothing of this type. And so the reason I chose this is to be able to make use of this fact that this type of dependent functions from BS2 into where the fibers are the underlying types of these two element types. Remember, that's empty. So this is going to be the same as, so this is not empty. And not empty, there's a single inhabitant of not empty, which is just the identity function on empty. And so this is a contractible type. This is a singleton type. And so so now my task is now reduced. So making use of this fact, I want to show that not all of this. So not 1 implies x of bs2, not x. And 1 implies something is the same as just that thing. So really I want to show not there exists x of bs2, not x. So that was a lot of steps. So let me pause. Did everyone did everyone follow kind of that calculus I did there? Okay. Not seeing any major objections, so I'm going to assume that makes sense. So so just kind of recap the everything so far. Oh, this question. What did pi x in bs2? I guess you're referring to this. So I made these choices, and so that instantiates for all a and a b of a to for all x in bs2 x, and so I know that that's equivalent. So for all x in bs2 x, that's empty type. I know that there's no function of that type, and so the stuff inside the parentheses here is equivalent to the empty type, and so this whole thing is equivalent to not empty type. So this whole codomain here is not empty type, and not empty type is equivalent to unit, because there's a unique term of type empty, arrow empty. Oh, okay, yeah. I think so the I think the comment that I made was that I'm writing here x of type bs2, and so really x is just the first component of bs2. So a term of type bs2 is a dependent pair of this x and an inhabitant of this truncated type here. But this is a proposition, and so for each x, there's at most one term of this type, and so so just for convenience, I'm going to kind of ignore that and just assume it's kind of floating around, and so I'm just going to write x of type bs2 to refer to just the underlying type. So I think that that's what I meant by that. Okay, so in order to get my refutation, I need to prove that there does not exist an x in bs2 such that not x. And so here I'm going to have to be more careful about what an x in BS2 actually consists of. So let me so I want to so now what my goal is that I want to show that if you can give me essentially if you can give me an x in BS2 whose type is empty, so there's no elements of type of the underlying type x, then that is absurd. And so the reason that this is absurd is because x being in BS2, remember, means that that x has two elements, and so if it has two elements, it doesn't have zero elements. Is the point here? And so so if I spell this out a little bit more carefully, this is saying that given a type u and given a actually let me write it out like this. So given a x and phi, which is of type BS2. So here I'm being careful about this, that x is the type and phi is the inhabitant of the truncated. I'm going to treat this as remember, bool equals x. So here phi is an element of type merely bool equals x. Then and then if I have not x, then that implies false. And so so I need to define this. So I'll say given given, or let me transform this one more time. So this is the same thing as a function from this iterated sigma. So this is a sigma over a sigma, so that's the same as two sigmas. So this is x in u, and really an easier way to write this out would be for all x in u, for all phi of type merely bool equals x, and then for all k of type not x, false. So writing out of a sigma type is the same as kind of just taking in all the arguments as pi's. And so now I'll say given x. So what this says is that given arbitrary x of type u, we need to construct a term of this type, phi from this truncated type to not x implies false. And so since we're mapping out, so this ends up being a proposition. So ultimately empty is a proposition. So I can work with, kind of take this out of the truncation. So I'll say, so I'm using the universal property of truncations. So I can assume that now I have a psi, let's say, of just type bool equals x. And I need to, and so I need to, so if not x, then empty. So sorry, I keep rewriting this, but let me rewrite it one more time. So what I want is, I'm going to go back to sigmas actually. So x and u and psi of bool equals x, not x. I want to send that into the empty set. So if I can define this, then I can do the same thing for the truncation. So then I use probably the truncation and get something of this type, and eventually work my way all the way back into to get the result I want. And the thing to notice here is that a sigma, I have this sigma of a type and then things that are equal to that type. And so this right here, I can contract. So this is going to be contractible. Because, yeah, this is just a basic fact, is that if you have this iterating sigma of x and bool equals x, then you can just replace x with bool. And so really what this finally boils down to is I want a function of type not bool, arrow, empty. And so this is a simple function that we I think we constructed at the very beginning of the course, that if I have a function of type bool arrow empty, then I can apply it at true, say, to get a term of type empty. So I have a term of type not bool, or this thing. So yeah, so then working backwards, if you have that, then you have this, then you have this, then you have this, and then ultimately, you have a refutation of this type that we wanted to refute at the beginning. And so that's part 4. Question 4. Yeah. So so maybe saying that these are contractible is not quite the right terminology. But this is a common tactic in homotopy type theory, that if you can is that you can kind of contract away these you contract away sigmas. So if I have so if I have something like, if I have I'll do this for kind of a generic type. So if I have some type A in the universe, and I have some little a, I'll say a naught of type A, then the type A prime of A, and proofs that so psi of that, proofs that A prime equals A naught, and then some P of A prime psi, that's actually equivalent to just P of A naught REFL. So we call this contracting away that here that I have, basically I have a point, and then I have a proof, that I have everything, a proof that everything is equal to my kind of center point. So this kind of behaves like it's contractible, and I can just forget about it and go to A naught and REFL. And so that's fundamentally what I'm doing here, is that instead of working with some mystery type X and having on hand a proof that bool is equal to X, I can just say, like, well, if X is equal to bool, then let me just work with bool, and whatever I can say about bool is going to be true of X as well. And so yeah, that's similar to here, is that anything you can say of A naught and REFL is going to be true of A prime and psi. It's going to be true of A prime and psi, because A naught is equal to A prime Okay. Yeah, so there's a question about like why yeah, why don't we have a term of type? Yeah, why don't we have this term of type? Or yeah, why is this fact true? Like, why aren't we able to yeah, kind of canonically pick an element of BS2? So, I mean, kind of the rough reason is that that's a kind of yeah, that's kind of a choice principle, as it were, in that you know, if I just give you a set and tell you that and give you a proof, you know, not the actual proof, but just a yeah, let me phrase it this way. So BS2, what BS2 is defined as is it's the type of two element sets, but there's not a specific order selected on them. So if I dropped these brackets, or if I drop these this truncation, so if it was just sigma x and u, fin2 is equivalent to x, then this would not be true, because what I could do is, so yeah, fin2 has two elements, 0 and 1, and so I could just define this. I could define an x and to, yeah, x and bs2 to x. I could just define it as, you know, get the corresponding this isomorphism, and yeah, get this isomorphism, and then apply it at 0. So that would totally work. And so yeah, you don't get this result if you don't have these truncation bars here. But what the truncation bars are saying is that we want to know that merely, I keep using this word merely, and you know, kind of what that means is that if I say something is merely true, or we have a proof that merely this, it means that we have a statement here, a proposition, a type, or yeah, a type, which we're thinking of as like a logical statement, which could have multiple different witnesses. So if x here is fin2, for example, then there's two equivalences. There's the identity function, and there's the flip-flop that sends 0 to 1 and 1 to 0. So we have some claim which is represented by a type that could have multiple inhabitants. And so when I say that merely that's true, it means I know that I have a proof that it's true, but I don't have a specific one. I just know that this type is inhabited. I have an element of its propositional truncation. And so what the truncation here is doing is it's saying that we want our type to have, we want to know that our type has two elements, but we don't want to say which one is the 0th element and which one's the first element, which is what's being achieved by these truncation bars. And so what this is saying is, and so that a consequence of that is that I can't always just pick the 0. I don't have like a canonical choice of picking the 0th one or picking the first one. All I know is that there are two, you know, merely I know that there's two elements, but I don't know, I can't pick one in particular. Okay, so yeah, not having construction as term makes sense, but the fact that we can't postulate one, yeah, that's fair. I think the kind of idea of type theory, or of this kind of type theory, is that we want to sustain this kind of computational thinking of how our computational thinking to our terms. We want them to have a kind of constructive computational meaning, and this would violate that. So yeah, if you just postulated a term like this, then I think that would end up kind of end up contradicting something, or it would end up proving that X already has to be a proposition or something like that. But yeah, it's a good thing to wonder about, and I can encourage you to kind of keep thinking about it and keep asking about it, and on the Discord if I didn't do a good enough job here of kind of making some sense of it. But hopefully I was able to help a little bit. Okay, let's go ahead and finish off then with problem 6. So that'll probably give the rest of our time. So Yeah, problem 6. I really enjoyed problem 6 because I'm a category theorist at heart, and problem 6 is kind of concerns a type theoretic analog of an important result in category theory called the Untitled lemma. So you don't need to know what the Untitled lemma is from category theory in order to understand this problem, but if you do, then hopefully you can kind of see why we call it that. Okay, so our basic setup here. So now I'm doing 6. Sorry if my 6s look like B's. I don't know how to fix that. So 6 says that, so our setup here is that we have, so U, we specifically says is univalent. I've kind of been using univalence liberally anyways, but you know, this is specifically a theorem about univalent universes. And then we have an A of our universe, so type A. And then we have a type family P over A. So P A to U. Actually, so we have some fixed A. And then the statement of the Untitled lemma is that for any A in A and any P over type family P over A, we have this equivalence that for all B and A of A equals B to P of B, functions of that form are equivalent to P, just P of A. And so the kind of general idea here is that if you want to come up with a form, a term of this form, then the only kind of natural way to for any to construct a P of B. So this is for any B. The only way to construct a P of B, only given B and a proof that A equals B. The only way to really do that is if you have a proof of P of A on hand, and then you can just transport along this equality to get a P of B. So that's basically what this lemma is saying. And so we're not going to prove this lemma, but you can prove it if you like. So this is the already YL. This is the Untitled lemma, which says that this is an equivalence. Okay, so now part A. So part A, so that's our setup. Part A says that we want to suppose, there's a key supposition here, suppose that this total type A and A, P of A, is contractible. So that'll just be, that's just our condition here. So there exists a unique A such that P of A, and there's a unique proof of P of A. So this is a contractible type. And so it says, now that it wants us to modify this statement, so that we already know this statement, we don't need to make this assumption of contractibility to get this statement, but we do need to assume this contractibility claim in order to turn this arrow here into an equivalence. So we need to show that this for all B in A equals B is equivalent to P of B. So this is kind of, if A is equal to B, then P of B. This is A is equal to B if and only if P of B. That's equivalent to P of A. And so, so let's do that. And so this is going to make use of an important fact that we've seen before. I think it's the exercises say that it's Theorem 11.1.3, and that says that if I have a family of maps for each B in A of A equals B to P of B. So this is a family of equivalences. So each of these is an equivalence if and only if the induced map on the total space is an equivalence. So if so we get a map sigma B and A of A equals B to sigma sigma B and B P of B is an equivalence. So fiber-wise equivalences are equivalences on the total space. And in the general statement, this doesn't need to be A equals B. This just needs to be some type family over B or over the type A. But it works for this. So here A is some fixed term of type A. And so yeah, so fiber-wise equivalences are equivalences on their total spaces. And the key thing to note here is that, and we kind of touched on this a little bit in the last section, is that this is contractible always. So the collection of those B's in A that are equal to A, that's just the center of contraction of that is A and REFL itself. So this is contractible. But then notice that we assumed our assumption here was that this is contractible. So here I wrote it with an A and A, and here I wrote it as a B, but that's the same thing. So this is contractible. So this we assumed, whereas this is always contractible. And so yeah, so we have two contractible maps. So any map from a contractible type to a contractible type is going to be an equivalence. And so yeah, so we have a so this ends up being equivalent. So therefore, this is a family of equivalences. And so yeah, so we prove that each of these, so under this assumption that this is contractible, then we get that that this is the same type. These are the same types. So we prove that all these are equivalences. So requiring them to be equivalences is the same thing as just a map. And we know that by the Oneida lemma that this is equivalent to P of A. And so we get that this is equivalent to P of A. And so that's part A. Is this the fundamental theorem of identity types? This is something I always screw up. I think this was just a lemma towards the fundamental theorem of identity types. But I could be wrong about that. Yeah. Okay, so then yeah, so then our last bit is we want to show so now we move on to 6b. So in B we're given this this type family id, which goes A to U. And so we think of this as a function from A to type families on A. And so the claim is that this is an embedding. So we want to prove that this is an embedding. And remember that what it means to be embedding is that the fibers are propositions. So being being an equivalence, it means that your fibers are contractible, whereas being an embedding is just that they're propositions. So you can kind of think of this as, so this is kind of a notion of surjectivity, or sorry, of injectivity. So having your fibers be propositions is a notion of injectivity, that there's at most one thing that, for each thing in your codomain, there's at most one thing in the domain that maps to it. And if moreover, each of these fibers are inhabited, that's kind of surjectivity. So yeah, this is how this is how bijectivity or injectivity and surjectivity is kind of generalized in homotopy type theory. There's a question. A couple questions. So I think so. The exercises specify that this fiber-wise equivalences are equivalences of fibers. That's theorem 11.1.3. So let me write that. So 11.1.3. I didn't check out that reference to make sure that's correct, but yeah, and I think this would this was I think this was an intermediate result in Emily's lecture on the fundamental theorem of the identity types. And so the so then there was another question: how does id have that type? So when I write id here, what that means is that id of a prime is defined to be a equals a prime. So it gives back the type a equals a prime. So yeah, so it takes two elements of, so I've fixed some type A here, and so it takes two elements of that type and gives back a type. So that's how it has that type. But we're going to be thinking of it as a function that takes in the first thing and then gives us back a type family over the second thing. Okay, so we want to prove that fibers are propositions. And so what that means is that for anything in the codomain here, so for any P from A to U, we want is prop of the fibers. So all of those A in A, such that id A equals P. Right. So this is what the fiber is that it's those things in the domain A, such that if I apply the function id to them, I get the thing I'm trying to hit in the codomain P. And so, one sec. Okay, so we're I'm going to follow the exercise or the posted solutions here and give this property a nice name, or give this give this family a nice name, and that's going to be the solutions call it is representable, but I don't want to have to write representable over and over, so I'm just going to call it is rep of P. So we're going to think of this as a property on A or U, is defined to be this sigma. So the sigma of A in A such that id A is equal to P. And so we want to show that for all P is prop of is rep of P. So we want to show that this is always a proposition. And Yeah, so one thing I wanted to remark before we get into that proof is that we can give an equivalent form for what is rep of P is. So so is rep of P, and there's a category theoretic reason why we call this is rep, but I won't go into that. So remember, we define this to be the sigma of A in A such that id A is equal to P. And so this is an equality of this is an equality of two functions. So both id A and P have type A arrow U. And so we can use function extensionality to expand this out as, so we still have a kind of a base point A and A here. And then we want to say that for all B and A, how do I want to say this? Yeah, for all B and A, id AB, so A equals B, is equivalent to P of B. Right, so this is just function extensionality. Is that so I'm also using univalence here. Is that an identity between functions is a pi type that for all things in the domain. If I apply the left-hand side and the right-hand side, I'm going to get equal things. So that would be A equals B equals P of B. And then I'm using univalence to turn that equals equivalently into an equivalence sign. So this is what is rep of P is equivalent to. And so I'm going to treat the elements of is rep of P to be pairs A and I'll call it eta, where A is of type A and eta is of this type. And so so yeah, with that in hand, then now let's go ahead and prove that is prop of is rep of P. So do this in pink. So take arbitrary P from A to U. And then, what we'll do is we're going to show that is rep of P implies is contour of is rep P. So this is an equivalent way to show, or this is one way to show that something is a proposition, is to show that if it's inhabited, it's contractible. So remember, kind of intuitively, the propositions are things that have up to equality, either 0 or 1 elements. And so if I show that it has at least one element, if it's a proposition, that means it has to be contractible. So this is one way to show is proposition. And so now we'll do, so to define a function of this, we just take an argument of this type. So we'll take, like I said, A and eta of type is rep of P, or really, I mean this sigma type here. So A is this and eta is this. And now we want to show that given that is contractible of is rep of P. And so we can actually just calculate this out. So let me switch colors again. So we can say is rep of P. So we want to show that this is contractible. That is going to be so by what we showed here, that's going to be equivalent to I think I'm going to change the letters a little bit. yeah, so we have some fixed A. So I'm going to use a different letter. I'm going to say this is equivalent to, yeah, I'll write B in A, and then the pi will go over C in A, so B equals C, equivalent to P of C. So this is this is just the result that we had for isrep. And then we're going to use our result. Oh wait, I skipped an important step here. So before we get to that, no, don't need that yet. Now what I'm going to show is that is contractible of sigma B and B, P of B. So I'm going to say that if P is representable, then so I'm assuming this proof A eta of is representable of P, then I'm going to show that the B and B such that P of B is contractible. Okay. And so the reason for this, so the reason for this is that so we have this eta. So eta is of this type, that for all B and B, A equals B is equivalent to P of B. And so this is a family of equivalences, remember. And so by that same theorem as before, which I have written down, I think here, that I have a family of equivalences if the corresponding map on the total spaces is an equivalence. So since I have eta, so let me change colors. So by this eta that we have, we can say that the map on these total spaces is an equivalence. So we have that the sigma B in A equals B, that's going to be equivalent to sigma B in A, P of B. So family of equivalences is equivalence on the total spaces. And then again, we're going to use this trick of saying that this is contractible. And so if it's equivalent to a contractible type, then it also must be contractible. So we have that. So we have this result that is contractible of those B and B, such that P of B. Okay, so now we can take the last step and prove that that is rep of P is contractible, which is what we wanted. So this will again just be kind of a calculation. So I have that is rep of P that is equivalent. Oops, one too many lines there. Is equivalent to the sigma B and A such that such that for all C and A, B equals C is equivalent to P of C. So that's what we had before by this result. And then did I say B and B somewhere? Oh yeah, this this should be B and A, I think here. There is no capital B here. Everything is in capital A. Sorry, thanks for that. Okay, so we have this, and then what we said is that, so let's go back to part A now. So part A says that if the sigma A and A P of A is contractible, then this sigma, this pi type here is equivalent to P of A. And so the so this so we proved that the sigma over p is contractible. That's what we did just in the last step. And so we get that this thing here, I can rewrite this as still have B in A, but now I can replace all of this with P of B. And then again, I'm going to use this result that I just showed, that that B and A such that P of B, that we show that that's contractible. And so this, I can write this as this is equivalent to 1. And so, oops, sorry, I've kind of gone off the edge here. And so this proves what I want. So I assumed that isrep is inhabited. So I assume there's something of type isrep, and then I use that to prove that isrep is contractible. And so therefore I can conclude that isprop of isrep of P. So if isrep of P is inhabited, then isrep of P is contractible. And so that suffices to prove the claim. So we have that isrep of P is, so kind of going back a little bit, we have that isrep of P is a proposition. And so that means that, so remember isrep of P is was the fibers of, or was the fiber of P under id. And so this shows that id is an embedding. Okay, hopefully that made some sense and was useful in some regard. And I was hoping to spend an hour and a half going over these problems, and it is exactly 1:30. So I'm happy to hang around if there's any lingering questions. Otherwise, yeah, thanks for coming. And I guess there won't be a next time. This is my last time doing one of these problem review sessions. So thanks for coming, and yeah, take care. Okay, I'm going to go ahead and stop the recording then, if there are no objections.